Human communication is fluid. When a person uses sign language, the meaning exists in the continuous motion, the transitions, and the timing. But if you try to feed that continuous stream into a static, frame-by-frame image classifier, the model completely loses the context of time. For Bengali Sign Language, or BSL, automatic recognition has historically struggled exactly because of this limitation. Early research restricted its scope almost entirely to small-scale datasets covering isolated alphabet signs. Legacy datasets like Ishara Lipi or Baus Lipi relied exclusively on static image classification. They captured the pose at a single fraction of a second, completely ignoring the temporal motion dynamics required to form actual words. If we plot the historical data landscape, mapping modality against scope, the gap becomes obvious. The existing datasets are tightly clustered. They are siloed into either image-based isolated characters or, more recently, video-based isolated words. Practical communication does not compartmentalize itself like this. To translate real speech, a system requires a unified temporal scope that can recognize alphabets, numbers, and words seamlessly within the same context. Treating these elements as separate classification tasks is an architectural dead end. To build a functional sign language model, researchers first had to construct a massive multi-class dataset built entirely on continuous temporal video. This bottleneck led to the creation of a newly proposed BdSL video dataset. The scale of the collection process was rigorous. 12 distinct signers generated 15,468 continuous videos, yielding nearly 13 hours of raw temporal data. This chart breaks down the 82 distinct classes captured in the dataset. It successfully unifies 43 alphabets, 10 numbers, and 29 specific words into one contiguous classification challenge. The dataset also deliberately introduces spatial variance. Every gesture was recorded from 3 different camera angles, left, front, and right, across varying indoor and outdoor lighting environments. This introduces an immense computational problem. Standard single-stream visual models collapse when forced to process this degree of combined spatiotemporal and viewpoint variance. Processing 82 classes of multi-view sequence data means we cannot rely on raw pixels alone. The model needs a system that can decouple the high-frequency visual details of the hand from the underlying structural motion of the signer's joints. This is the architectural schematic for the BSL MoEFormer, built to process visual appearance and motion simultaneously. Looking at the initial pre-processing module, the model splits the input. The first track extracts features from video into tubelet embeddings, while the second track isolates structural motion, outputting a separate pose embedding. Single-stream CNNs historically fail because they over-index on raw RGB pixels, causing catastrophic classification failures when the camera viewpoint shifts. To correct this, the architecture implements a pose-guided fusion module to bridge the visual and skeletal streams. This forces the structural, viewpoint-agnostic pose data to actively guide and constrain the high-dimensional visual feature extraction. Mechanically, the module uses cross-attention and gated strategies to blend the RGB tokens with the structured pose embeddings. The skeleton essentially tells the network which spatial regions in the video actually matter. By forcing raw pixels to submit to structural skeletal constraints, the model achieves true spatial disentanglement, rendering the initial camera angles irrelevant. Once fused, multimodal tokens enter a 6-block transformer encoder. But processing 82 distinct motion patterns through a standard dense multi-layer perceptron requires massive, inefficient parameter scaling. The architectural pivot happens in stages 3 and 4, replacing dense blocks with a sparse mixture of experts module. This introduces conditional computation. Instead of activating the entire neural network for every single frame of a video, the network dynamically routes the data. As the tokens arrive, a routing node evaluates them and selects only the top 2 out of 8 available expert networks to process that specific motion token. This specialization allows subnetworks to master specific sign types. One expert processing sharp, rapid digit movements, while another handles fluid, sweeping word gestures. This configuration decouples model capacity from compute cost. The architecture gains massive representational intelligence, yet because only a fraction of the parameters are active at once, the system remains computationally lean during inference. Sparse MoE acts as a task-driven scaling mechanism, allowing the architecture to possess high representational capacity without paying the dense computational tax. However, scaling capacity introduces a hidden danger in deep transformer networks. As these multimodal tokens interact across multiple layers, traditional residual connections begin to destabilize. To maintain structural integrity, this architecture integrates manifold-constrained hyperconnections, or MHC. Looking at these diagrams, a standard residual mapping compromises its identity mapping property when handling highly diversified connectivity. MHC addresses this using a manifold-aware token mixing formulation, utilizing specific pre- and post-mapping constraints. Conceptually, it introduces a learnable token mixing matrix designed as a low-rank factorization. This matrix is mathematically normalized using Sinkhorn iterations, forcing a doubly stochastic mixing property across the tokens. For the BdSL MoEFormer, this stabilization step is absolutely critical. It restores identity-preserving behavior while permitting the highly subtle motion dependencies of sign language to propagate cleanly through the deep sequence. MHC provides the mathematical rigidity required to map the high-dimensional manifold of fused pose and pixel data, ensuring the model trains stably at scale. Finally, we follow those stabilized encoded tokens out of the last transformer block and into the extraction phase. The final classification head projects the ultimate target token down, predicting the exact Bengali sign out of the 82 unified classes. This chart displays the quantitative results of this rigorous system design. When tested against the challenging multi-view, multi-environment dataset, the model achieved an accuracy of 82.9%, with precision at 81.0%, recall at 81.3%, and a final F1 score of 82.3%. Maintaining an 82.3% F1 score across 82 continuous video classes validates the complete pipeline, from the initial tubelet extraction all the way through to the MoE scaling. And this performance holds up despite the constant shifting between indoor and outdoor environments and 3 distinct camera axes. The immediate next step for this technology is expanding the temporal window, moving from isolated sign detection to continuous fluid sigence level recognition. There is also a deployment challenge to solve. Researchers must now explore lightweight versions of this architecture, specifically designed for real-time edge translation. Further ablation studies will also be necessary to strictly quantify exactly how much the MHC residual and the top 2 MoE routing individually contributed to that final F1 score. But the core achievement here stands, successfully unifying alphabets, numbers, and words into a single manageable tensor space. The development of the BdSL MoEFormer demonstrates how integrating dataset design with specialized architectural modules can bridge the gap in underexplored sign language domains. By aligning the data's multi-class complexity with a targeted multimodal pipeline, it establishes a benchmark for robust